Part 2 of the calorimetry section contains 3 examples. I left it in the earlier PowerPoint, but I did not talk about it because I wanted to have time. So when we're talking about calorimetry, we know that the container is going to affect the transfer of heat. If we were in McPherson 1000, I would have brought in my cup of tea, or I'll call it a beverage, like they would in a big bang, and I would walk up and down the aisle and say to people, oh, does this cup feel hot to you? I would touch some people's, coffee, and they'd say also, this is hot. Well, that's what we want you to think about. Think about a cup of hot coffee. The coffee is hot, but the cup is also hot. That means if we're talking about doing measurements, we need to account for what energy is going into the container. So we've got our 2 terms from our earlier calculations, and now we have added in a calorimeter. And that calorimeter number, it can be used to find out the heat capacity. Now, heat capacity is 2 words, but they tend to abbreviate it just as AC. Before you faint, this is all information that is given. Please pause, take a look at it before you proceed on. It gives you the 3 pieces you need to calculate the Q of the zinc. It gives you the 3 pieces you need to calculate the Q for the water. Since you'll have the Q for the zinc by doing all of this, since you'll have the Q for the water by doing all of this, you can find the Q of calorimeter. Buried on the bottom here, hard to see, is my T final, okay? So we have 2 initial temperatures and a final temperature. Let's move on to the actual calculation. We know that the heat lost by the zinc, it has the negative sign. It's going to be equal to the heat gained by the water. There's the water, and also the heat gained by the calorimeter. Pause, because there's just a lot of information here until you get your hands around that. Now, just like we said on the slide before, we have everything we need to calculate the heat for the zinc. Specific heat, mass, temperature change, and in this case, the temperature change is 92.9 degrees centigrade, and it's going to give us a value of negative 730.82 joules. We will do the exact same calculation for water. Here we have the water. Our specific heat, our mass, our temperature change of 2.1, it's going to give us a 701.68 joules. Having those 2 numbers, we can now, and I hate to call this equation 3, but I shall, and I'm referring to the entire equation. Here we have equation 3 about midway down the slide. We've placed in our calculation from number 1. We've placed in our calculation from number 2. That allows us to find the Q of the calorimeter. So I'm kind of going to draw a line here because I've taught this a number of times, and just getting through this part requires quite a bit of thought if you've never done it before. So to recap, the heat that is lost by the zinc is equal to the heat gained by the water and the calorimeter. But we're really looking for the heat capacity. We are looking for the C. And the way these are related is the heat of the calorimeter is the heat capacity of the calorimeter divided by the temperature change. So I rearranged this equation, 4C, gave you an extra equal sign. Here I put in my answer from calculation number 3. Here I put the delta T for the water. That's the one we use for this calculation. And I come up with a heat capacity of my calorimeter of 14 joules per degree centigrade. That means if I want to run another experiment, I can use this value as a correction factor when I'm looking at my heat of water, or let's say heat of reaction. Well, heat of reaction kind of takes us to the next example. Example number 2 is called constant pressure calorimetry. And when you want to be very, very precise, you're going to use an electrical source to generate a known amount of heat. You're not going to mess around with the things we did in examples 1 through 3. So here is the problem at hand. We have some barium hydroxide. We're going to react it with ammonium nitrate. We're going to make some barium nitrate in water, as well as produce ammonia and some water. So ammonium nitrate, very unstable material, and that is exactly what happened in Beirut when whatever touched off that explosion. 2 steps to solve this problem. The first is, what could the temperature change be? Well, we have our final minus our initial, and we come with a value of a negative 38.5. The temperature is falling. Once we have determined that, we can move on to number 2, because Q is equal to the heat capacity, which is given. We've just calculated the temperature change, and it allows us to come up with the heat for this process. Now, the second step we're going to show for this is identical to what we did with our aluminum and iron oxide earlier in this example. So I back up just a little bit. I said, well, the heat lost by the solution, that would be the minus 6233, is going to be equal to the heat gained by the reaction. That means that we will have a positive number for our delta H of reaction. I wrote the equation above it. I don't know if I really had to or not, but there are things to point out. The molecular weight, okay, I guess I should back up a little bit. This is my sample size. This is my calculated value. This is my molecular weight, and it includes those 8 waters of hydration. So we talked about that back in chapter 2. So all these things are a prelude to what you do now. And the reason that I put the reaction back up is because there is a number 1 in front of the barium hydroxide octahydrate, okay? So 1 mole of the barium species for every mole of reaction. And if I look at what number am I going to get when I do all the work, I'm going to get 62231 joules, which is equal to 62.2 kilojoules for this reaction. It's a very, very, very exothermic reaction. And the heat that's lost by the solution is the heat that is gained by the reaction. So again, this is a longer problem. It's the second of 2 examples, and we wrap up this section with the 3rd example. And it is called a bomb calorimeter. When I mention a little bit about calorie content of food, they run these reactions, and the vessel they use is a bomb calorimeter, which was pictured on our first slide when we began 5.5. So if you're going to have gases, what you really need to do is have everything contained so that you are at a constant volume. You do not let the volume change so this delta H relationship can hold. No PV work is done. Any heat that's absorbed or evolved, it's going to be changing the internal energy of the system, that delta E, which was Q plus W. Remember back, delta E was equal to Q plus W. We don't have any W, so all we have is Q. And I used 2 slides for this one also. Here we have a sample of boron hexahydride, or people just call it a boron hydride. It's reacted with excess oxygen in a bomb calorimeter. We're given the heat capacity and the temperature increase. We don't have to do a delta T. It asks us to determine the delta H of reaction, and the details are given on this last slide. First, you want to calculate the heat gained by the calorimeter. Here is our heat capacity. That is our temperature change. Here is our heat capacity. I know I should be using a C. And what we have is a heat of 26.03 kilojoules. Now again, you will recognize the end of this calculation from our aluminum Fe2O3 example. So what we have are a number of kilojoules, and we have heat gained, then it would be the heat from the reaction, so we change the size. We have the sample size, the mass. We have the molecular weight. And I didn't repeat it, but once again, you look at the actual stoichiometry and you see there is only 1 mole of B2H6 for every mole of reaction. And even though we had a milligram sample, 336 milligrams, it gave off 2,143 kilojoules of heat. This is actually what they put in rockets if they want to send them into outer space. So this wraps up calculations and calorimetry. No one that I've ever taught has honestly enjoyed them. Please take some time, teach yourself to do them, work some homework problems, work some sample problems. And as usual, please ask questions.